Hello everyone, this is Power System. Welcome to class number 12. In this class, we're going to talk about transmission line model, especially short and medium length line. So in the last chapter, we talked about transmission line parameters, basically how to find resistance, inductance, and capacitance of the line. So as you know that resistance and inductance, they're in series with a line, and capacitance could be line to line or line to neutral. For the transmission line modeling, we use line to neutral capacitance model. So we're going to model one line to neutral. That means we're going to take one line which has resistance and inductance, and we're going to take a capacitance from that line to the neutral. So this is what I'm talking about here. So you can see that we have three line A, B, C, and neutral. We have R, and we have L, we have C. The C is line to the neutral for each line. So, and this R, L, and C, they're per unit length, right? So to find a section of 10 miles, you have to multiply by 10 mile for each of the parameters, right? And same the capacitor, same with the inductor, right? So if I take a section right here, this section right here, if I take this section over here and bring it down here, that's the transmission line model. We call this lumped parameter model because you're lumping this parameter together. It's called lumped parameter model. So we're lumping, if the section length is 1 kilometer, we're gonna have the whole R and L together for 1 kilometer. It could be 10 kilometer, could be 150, 200 kilometers. You're gonna put them together in one section. That's the lumped parameter. And that is the, we also call this pi model. It's look like a pie, so we also call it pi model. All right. Now, for the short line model, this is the equation for capacitance in transmission line to the line to the neutral. And you know that for small distance, this capacitance will be very small. Like short line is less than 50 miles or 80 kilometers. So this capacitance value will be lower. Also, short line has lower voltage. So with these two parameters, C is smaller, line to neutral voltage is smaller, your charging current would be smaller, that we can ignore it. If you can ignore the charging current, also you can ignore the capacitance here, right? So this capacitance could be ignored. I'm going to erase them so that your model look like this. It's very small series circuit now. So your VS would be VR, which is receiving end voltage, and it's a sending end voltage plus loss in the line. And also your if you know how to find the three-phase complex power at the load is SR over here is 3IR VR because these are phase to neutral quantity. So that's I have to multiply by 3, and this is the conjugate to find complex power. So this three-phase power is given. You can easily find the current going into the load in the receiving end. Remember that in power system problem, all the power will be given in three-phase power, and all the voltage will be given in line to line voltage, and all the current will be given in line current. So if you need line to neutral voltage, you have to find it. You have to, if you need any other current, you have to find it, and you also need to have single phase power. You have to find it from the three-phase power. So that's the equation for your voltage relation between sending end and receiving end. And your current, if you go back here, so these two currents are equal to each other, right? IS equal to IR, it's right here. So also I can, to match with this equation over, I can say 0 VR over here. So if I now compare with this equation over here, this is so-called ABCD constant of the transmission line. We model a two-port network with ABCD constant. So your A is B1 here, your B would be Z over here, right? A would be 1 if you equate them, B would be Z here, C is 0, and D is 1. That means now if you know ABCD constant, you can make a matrix from this equation here. If you know ABCD constant, you can easily find the relation between receiving end quantities and sending end quantities. And also from here, you can also find receiving end quantities by taking the inverse of the matrix. All right. So ABCD constant is the prime goal here to find ABCD constant in transmission line. Then you can find the relation between sending and quantity and receiving end quantity. So voltage regulation is another thing you have to pay attention here. That means how much voltage is changing in between two extreme case. Two extreme case should be full load to no load. So full load means you're supplying whatever required load here, and no load means you are disconnected. No load means you are disconnected, so there's no current going in. So that means your voltage VR would be different here, right? So what about the VR? You know this equation, Vs equal to A VR plus BIR. So no load, your current is 0. That means your VR no load would be Vs over A. Vs is sending end voltage. Normally, no load voltage is higher than your full load voltage. So then you'll find the difference between them over here. Then find a difference with respect to percentage. We want this percentage less than 5%. Voltage regulation need to be less than 5% between extreme cases. All right. And voltage regulation, again, it depends on what kind of load you're supplying. If you're supplying a lagging power factor load, then your sending end voltage and receiving end voltage, there's a relation here, sending end voltage is higher than receiving end voltage. And you're supplying a load with lagging power factor, so that's the relation here. You're supplying a load is leading power factor, that's the relation here. Vs could be smaller than VR. All right, and also your root regulation will depend what kind of load you're supplying. We're going to do this problem in the class. Let's talk about the medium line model. Medium line model is basically your line is between 50 miles to 150 miles. If you have that length, your voltage increases as well as your capacitance value increases because of the length, so you cannot ignore them anymore. So if you cannot ignore it anymore, you have to add them there. So over here, you see a new symbol Y. Y is basically your opposite of impedance. It's called admittance, 1 over Z. Z is the impedance, right? So if your XC is 1 over J omega C, Y could be J omega C. And Y is also for the total length, so you can multiply with the length. So find a Y value for the whole length. All right, Y value for the whole length. And what is G over here? G is conductance. We assume that there is no current conduction between line because of the low resistance between them. So that's why conductance is 0. That means you have basically the resistance between line or line to neutral is really high. It's open circuit, so conductance is 0. So with this, this is the model for the medium line. We cannot ignore the capacitance anymore. So we get the capacitance for the whole line. Let's 150 mile line. So get the capacitance for the whole line and divided them on both sides to match with our model. So now, with the model, if I apply KVL at your receiving end, I get IL is coming in, IR, and current in this branch over here is this. So current is what? VR over Z, but over here, the impedance is Z is 1 over Y, so it's Y over 2. We're multiplying it Y over 2. That's why is the current over here Y over 2 times VR, because admittance is the inverse of impedance, right? So that the current and the voltage is very small, simple KVL, VR plus what the loss in the line. Now, if I combine these two equations, I'll get this equation over here. Then for the sending end current over here, IS equal to the current going to this branch over here as well as current coming here. So IL plus Y over 2 times BS. Again, when you have admittance, you multiply with the voltage to find current because it's the opposite of impedance. Then if you substitute IL and IS and VS value over here, you will find this equation for IS. Now over here, if you compare them with the ABCD constant, this is your C, this is your D, this is your B, this is your A. So if I come back over here, I have A, B, C, D constant already written over here. And from this matrix, I can find sending end voltage if receiving end voltage are given and current given. Also, I can find vice versa. I can find receiving end quantities if the sending end quantities are given. All right. So main goal here to find A, B, C, D constant. and we're going to do this problem in the class. So come back to class with these materials reviewed, then we can do the problem.